In the last class, we learnt about the thermodynamics of solids. We learnt about how the Gibbs free energy of solids and liquids changes with temperature, and when you are below the melting temperature, the Gibbs free energy of the solid is lowest. So, we also learnt about phase diagrams. Now, today I am going to talk about crystallization kinetics, that is, what is the rate of crystallization, what is the rate of solidification. Let us first just refresh what we learnt about the phase diagram. So, if we look at the pressure temperature phase diagram for any material, then what we saw is that there is a solid phase, a liquid phase and a vapor phase. So, this was the vapor, this was the liquid and this was the solid. And what we said was that you can take that if you start at some point, let us say you start in a liquid, you start at some point here and you move towards this, you move in this direction, that is, you lower the temperature of the liquid. When the temperature of the liquid becomes smaller than this temperature, then the liquid will solidify. So, when the temperature of the liquid crosses this line, then it will solidify. Okay. So, and what we say is that along this line we have the Gibbs free energy of the solid is equal to the Gibbs free energy of the liquid. Okay. So, along this line, anywhere on this line, anywhere at this line corresponds to certain values of pressure and temperature. So, at those values you will have the Gibbs free energy of solid and liquid be the same. So, now we can see that the Gibbs free energy is of the solid is equal to Gibbs free energy of liquid at the melting temperature, and it should be kept in mind that the melting temperature depends on the pressure. Melting temperature at different pressures changes. Okay. Now, below Tm, below the melting temperature, the Gibbs free energy of solid is less than Gibbs free energy of liquid. So, the solid is the more stable phase below the melting temperature. So, now it should be kept in mind that below the melting temperature the liquid itself is not stable. So, but if you imagine as a function of temperature calculating the Gibbs free energy of the solid and the liquid, okay, you will see them cross each other. So, you might see the Gibbs, you might see that this is the Gibbs free energy of the liquid, this is the Gibbs free energy of the solid. Okay, and I am just imagining that if you had any material, then typical curves for the Gibbs free energy as a function of temperature would look like this. So, the liquid would typically be higher than the solid at low temperature and it would go below the solid at higher temperatures. Where they cross, this is the melting temperature. So, that is when the Gibbs free energy of the solid and the liquid are the same. And it should be kept in mind that I am doing this whole thing at some fixed pressure. So, as you can see here in this region, clearly Gibbs free energy of the solid is greater than Gibbs free energy of the liquid. Here Gibbs free energy of the solid is less than Gibbs free energy of the liquid. Okay. This is the basic idea of crystallization. So, you and what you should keep in mind is that the solid here is actually not stable. Okay. So, this is unstable, and that is why it is so you will never actually see a solid. So, this is just a hypothetical state. So, the solid in this region above the melting temperature is just a hypothetical state. So, what we mean really is that if you had a solid at this temperature, then its free energy would be greater than that for a liquid. Similarly, the liquid at this state is not is a hypothetical state. Okay, so that is also unstable. So what you again mean is that if you had a liquid below the melting temperature, its free energy would be higher. Okay, now it's a question. Now obviously you do not have a liquid below the melting temperature. You do not have a solid above the melting temperature. So what do these numbers really mean? And you can think of them as some sort of model calculation. So you model a liquid, okay, and you try to extend its free energy below the melting temperature, or then you would get these curves. Similarly, if you model a solid and you calculate its free energy and extend that model above the melting temperature, you would get some curve, and this is representative of that. So these are purely representative cartoons, okay, and but they illustrate one interesting point, that that this free energy of solids and liquids, they will typically cross each other at melting, okay, and so you can imagine that if you are at some temperature, okay, so suppose you are at some temperature below the melting point. Let's say you are at this temperature. So you are at some T less than T melting. So at this T less than T melting, okay, as you go lower and lower, then the difference in the free energies of the liquids and solid increases. Okay, so you can see that delta G, okay, this is equal to G liquid minus G solid. Okay, this delta G increases as T decreases below melting. Okay. So as you take T lower and lower, okay, it becomes smaller and smaller, and in fact you can say that this delta G, okay, will go as Tm minus T. So as this T becomes smaller, okay, it will go, I mean it will keep increasing with this. So it's an increasing function of how much lower than melting you are. So this is the temperature below the melting. So how much lower your temperature is than melting. So if it is much lower than melting, then this quantity will be large and this delta G will be large. Okay. So you can think of this delta G, this difference in free energy, as a driving force towards crystallization. In other words, what we are saying is that the reason the material crystallizes when you are below this temperature is because delta G is greater than 0, and so if you want to imagine how fast it is crystallizing, then you could easily imagine that there is a quantity like delta G which tells you how much lower than the melting point you are, and that tells you how fast it will crystallize. Okay. Now again there is a difference, because what we are interested in is the rate of crystallization. So we are interested in actually the rate of crystallization. Okay, and the rate of crystallization, this is a question about the kinetics. Okay, this is actually a question about kinetics of crystallization. Okay, so what we say is that it's probably best to show this through a little illustration. So if you have a system, and this side you have a solid and here you have a liquid, okay, and this is just you imagine that some part of the system has become a solid and some part has become a liquid. Okay. Now what is happening is that some of this liquid is getting converted to solid and some of this solid is getting converted to liquid. So, the liquid freezing to solid and the solid melting to liquid are both taking place, okay, simultaneously, and so you have solidification and melting. These are competing processes that are taking place simultaneously, and the net rate of crystallization is the difference between the rate of solidification and the rate of melting. Okay. So, you can write that the net rate of crystallization is the difference between the rate of solidification and the rate of melting. So, that clearly tells you how many what is the rate at which crystallization is taking place, or the net rate of crystallization. Okay. Now, we can ask a little more questions about what happens during crystallization. Okay, so let's take the case of solidification, where the liquid is getting converted to solid. So I'll use the word solidification here. And I'll call this melting. So during this solidification, you have some atoms in the liquid which are in the liquid state. So if you take your particles that are particles, if they are atoms or molecules, they are in the liquid state, and what is happening is that suddenly a collection of particles, they arrange themselves and they go to a solid state, they go to some ordered lattice. Okay, you have a collection of particles that are suddenly arranging themselves and forming a solid like ordered structure. Okay. Now, in order for this to happen, these atoms have to execute certain motions. Okay. So if you take any atom in a liquid, typically it sees lot of atoms around it, and it has to essentially push them a little bit so that it arranges into the form of a solid. Okay. So there is an activation energy going from this liquid state to this solid state. Okay. If you look at the actual process of solidification, then it has to nudge all the things around. So any atom or a group of atoms have to rearrange, and there is some activation involved with that. So you can say that the rate of solidification has some activation energy, and that is given by E activation of solidification. So S here stands for solidification. Similarly, the rate of melting will also have some activation. So if you have a solid and it has to become a liquid, then this solid has to break some of the bonds that it has, and then it goes into a liquid. So there is an activation for melting. Okay. Now, if you are below the melting temperature, okay, then you can imagine that the activation energy for solidification will be smaller than that for melting. In other words, it is harder to melt than to solidify. Okay. So, and that is the reason you form the crystal in the first place, and again this is below the melting temperature. So, you can write this, you can take this factor of e to the minus as by kBt outside, and you can write this as 1 minus e to the minus delta mu by kBt, where delta mu is the chemical potential difference between the solid and the liquid. Okay. Now, I should mention that the nu, this is a prefactor, and this is a very typical kinetic expression for any activated process. So the first term, if you look at it, it is a nu multiplied by e to the minus as by kBt. This is an Arrhenius like expression. Okay. So this whole thing is an Arrhenius like expression. And the reason we use an Arrhenius like expression is because we said that solidification is an activated process. That means there is some activation energy involved with it. Similarly, melting is also assumed to be an Arrhenius like expression. Okay. So we are assuming that melting is also an Arrhenius like expression with the same prefactor. Okay. So, the assumption, the crucial assumption is that both solidification and melting are Arrhenius like processes, and both of them have the same prefactor. Okay. And if you remember your elementary kinetics, you learnt that this prefactor is related to some sort of frequency of oscillation. So, it tells you how these atoms vibrate either in the liquid or the solid. So, there is some fundamental vibration frequency which sets this prefactor. Okay. And in this simple picture, we are just assuming that both of them are the same. Okay. Again I should emphasize that this is just one very simple way to look at the rate of crystallization. Okay. It is a very generic way, but it is a highly simplified expression. Now, so we can write this difference as in terms of delta mu, where delta mu is essentially the free energy of liquid minus free energy of solid, or the molar free energy, which is the chemical potential. So, the chemical potential of liquid minus solid, and if you are below the melting temperature, the liquid has a higher chemical potential than solid. So, delta mu is greater than 0, and so this is the rate. Okay. And if you go to very low temperatures, then the free energy of the chemical potential of liquid is much greater than that of solid. Okay. And so this quantity becomes very large, or this delta mu becomes large, and so e to the minus a large number goes to 0. So, the rate becomes just given by this, rate is just given by this factor. Okay. But and if you are very close to the melting temperature, okay, if you are very close to the melting temperature, then this quantity becomes very small. Okay. And you can do what is called a Taylor expansion. Okay. You can use the fact that e to the x approximately equal to 1 plus x for small x. Okay. So, when x is less than 1. So, when x is very small, then you can use such an expression. So basically you can see that r, okay, so you have 1 minus e to the minus x. So that will just give you 1 minus e to the minus delta mu by kBt. So this whole factor will just be approximately. So you have the nu e to the minus Es by kBt, and you have a factor of delta mu by kBt. Okay. So in other words, the rate is proportional to the chemical potential difference. Okay. And this is a very useful picture. So if you go back to what we said in the last slide, we said that this difference in chemical potential, the delta G, which is G liquid minus G solid, okay, which is essentially the molar part of this difference is the chemical potential. So this is a driving force. Okay. And in this simple picture, we see that the rate, okay, for small temperatures is proportional to this quantity delta mu. And further you can show you can analyze this, and you can show that this rate is actually proportional to this delta T. Okay. How you can consider again for small temperatures, you can show that this rate looks proportional to delta T. Okay. Now, so this is the process of crystallization from a melt or from a liquid. So here you have a liquid and it's converting to a solid. Okay. You could also have crystallization from vapor. In the sense, what you have is your crystal is growing because there is a vapor, okay, of the material. Okay. Now, suppose you have a solid and you have a vapor above the solid. Okay. What we are looking at is you're looking at deposition from the vapor, and you have and you have desorption from the solid. So you have these two processes, adsorption of vapor onto the solid and desorption of solid onto the vapor. Now again, if we look at the phase diagram, the PT phase diagram, okay, the liquid, you have the solid, you have the vapor. Okay, so what we imagine is that we are going in we are going like this in this case. Okay, so you imagine that you have a vapor at and this is typically at very low pressure, and you increase the pressure and you will end up with a solid. So in this case, the vapor pressure is greater than the equilibrium vapor pressure. So if you have a solid and a vapor, okay, then there is always, whenever you have a solid, okay, there is always some equilibrium vapor pressure. So the vapor pressure is the pressure, okay, at equilibrium. So you have a vapor of the same material as the solid that has some equilibrium pressure. That means if you take any solid, there will be some vapor on top of it, and P equilibrium is the pressure of that vapor. Now suppose the pressure of this vapor was much greater than P equilibrium, okay, then what would happen is some of the vapor would solidify and it would form the solid. So you can work this out, okay. So the rate of adsorption and desorption, okay, it gives the net rate of crystallization. So the net rate of crystallization in this case works out to be the difference between the rate of adsorption and the rate of desorption, okay. And I am not going to work this out in too much detail, but you can show, okay, from very generic arguments that the rate of crystallization should be proportional to the difference between the actual pressure of the vapor and the equilibrium vapor pressure. So obviously if the pressure is equal to the equilibrium vapor pressure, then the solid and vapor are in equilibrium and there will be no crystallization. But if the pressure of the vapor is greater than that of the equilibrium vapor pressure, then the solid will crystallize, okay. And you can again connect this to the chemical potential difference, okay. Now when you go from a point, okay, that is, let us say along this line you have Ps or P equal to P equilibrium. So the pressure is equal to the equilibrium vapor pressure, okay, and again the equilibrium vapor pressure depends on temperature. So along this line, this pressure is equal to the equilibrium vapor pressure. Now if you imagine looking at the difference in chemical potential between one state that is here and one state that is somewhere here. So we are imagining that we are increasing the pressure, we are putting P. So in this region P is greater than P equilibrium, and in the lower region P is less than P equilibrium. So on this line you have P equal to P equilibrium. So right along, it is only along this little line that you have P equal to P equilibrium, along this line, okay. Above this line you have P is greater than P equilibrium, below this line you have P less than P equilibrium, okay. So now you can calculate the difference in chemical potential, okay, between a solid and a liquid. Now the chemical as in terms of the pressure, okay, and so the difference in pressure between a gas at or the change in chemical potential is mainly due to the change in pressure of the gas, because the chemical potential of the solid is not really dependent on pressure. So the change in chemical potential is only due to the change in gas, and if you just use a ideal gas law, then the difference in chemical potential between a gas at pressure P and a gas at pressure P equilibrium is given by this quantity. Okay. And in this case also the rate, okay, can be written as proportional to delta mu. Okay. So, the rate works out to be proportional to, approximately proportional to delta mu for pressures close to this P equilibrium. Okay. So, again we see that the driving or the rate of crystallization, okay, depends on this difference in chemical potential. Okay. And the difference in chemical potential can be calculated by the difference in pressure. Okay. So, now the other common case that we consider is crystallization from a solution. Okay. So, here we are looking at crystallization from a solution, and during crystallization from solution, what you have is you can imagine that you have a solution and you have some part of a solid in that. So, this is a solid. Now, if the concentration of the solution is C is the concentration of the solution. Okay. Now, in order for it to solidify, the concentration of the solution has to be greater than the concentration of a saturated solution. So, the saturated solution means that you cannot put any more of your solid in the solution without it crystallizing. So, the saturated solution is what is called the has a concentration of C equilibrium. Okay. So, this is your saturated solution. So, in other words, in the saturated solution your crystal and your solution are in equilibrium. Okay. So, and so in this case the rate, okay, again you can work this out from very elementary theories. This rate is now proportional to the difference in concentration of the solution and the equilibrium concentration. So, the equilibrium concentration is basically the concentration of the saturated solution. So, how much the concentration of the solution is greater than that of the saturated solution. Now, you know that you cannot make a solution more concentrated than a saturated solution. So, actually we say that so the crystallization will only take place when the solution is supersaturated. So, we call this supersaturation, okay, which is saying that the concentration is actually greater than that of the saturated solution. Okay. And in this case you can write the chemical potential difference between the solution and the solid is approximately given by kBT, the natural log of concentration divided by the concentration of the saturated solution. And sometimes we define a quantity called a supersaturation, which is this ln of C by C equilibrium, and this supersaturation is equal to 0 when C equal to C equilibrium. So, sigma equal to 0 when C equal to C equilibrium, and when C is greater than C equilibrium. So, sigma equal to 0 when the concentration is equal to that of the saturated solution, and sigma is greater than 0 when the concentration is greater than that of the saturated solution. And again you should remember that that is not an equilibrium solution, and that is why it crystallizes. Okay. Now, so this idea of supersaturation is quite interesting, and what you can see is that the delta mu or the difference in chemical potential is proportional to this supersaturation. Okay. Now, the solution is now on a practical note. How do you make a solution supersaturated? How do you put more things? How do you have a solution whose concentration is greater than that of the saturated solution? One way in which this is done in practice is by actually changing the temperature. So, you have a solution, you have a saturated solution, and you suddenly cool it. Okay. Now, what happens is that when you cool it at a lower temperature, your saturated solution concentration actually becomes lower. Okay. So, in other words, C equilibrium is a function of temperature. Okay. It depends on temperature, and C equilibrium at higher temperatures is higher and at lower temperatures is lower, which makes sense that if you have a higher temperature, then you can dissolve more material. If you have a lower, so the concentration of the saturated solution will be higher. So, suppose you suddenly lower the temperature, then you are undercooling it, so you use the phrase undercooling, okay, which says that you are below the equilibrium temperature, okay, and that makes the solution supersaturated. So, it is again out of equilibrium. Okay. So, this is one way of growing crystals from solution. Now, one of the things that we see in practice is that your kinetics of the crystallization may be very slow at low supersaturation or undercooling. So, let us say you have a solution and your supersaturation is small, that means you have a concentration just slightly greater than the saturated solution. Then the kinetics of crystallization is often very slow, and this is something that you have seen when you do your chemistry labs. Whenever you are crystallizing some, let us say you prepare some compound, maybe organic or inorganic compound, and then you have it in a solution, and you let the solution cool down, and you wait for it to crystallize, and sometimes this crystallization is very slow. Okay. The reason crystallization is slow, even though you are below the melting temperature, is that there is something called a nucleation barrier towards crystallization. Okay. So, how this arises is the following. So, if you have let us take the case of a simple, you have a liquid, okay, you have a liquid, and now in this whole liquid, okay, there is, let us say, a small part of the liquid somewhere here, okay, becomes a solid, and I will just show some piece that has become a solid, and you have liquid all around. Okay. So this is your liquid, and you have a solid here. Now, if this solid is well, okay, so we'll say that if you look at and you are below the melting temperature, so we say that the Gibbs free energy of the solid is less than Gibbs free energy of the liquid. Okay, so you are below Tm. Okay. So ideally, so what you would expect is that the whole thing will become a crystal. Okay. However, when crystallization starts, you start with a small piece becoming a crystal, and then bigger and bigger crystals forming. So crystallization starts from a very small crystal which keeps growing. Okay. Now, if you have a small crystal, then it has a bulk, which is a volume part, and it has a surface part. Okay. Now, the atoms or molecules that are on the surface, okay, they actually are not as coordinated as the atoms in the bulk. So the atoms in the bulk are connected to all the other atoms. They are bonded to atoms on all sides, but the atoms on the surface, okay, they see a liquid on one side and they see a solid on the other. So there is a tendency of these atoms to go into the liquid. Okay. In other words, there is an interfacial energy associated. So this interface between the solid and the liquid, okay, that actually costs some energy. Okay. So if you look at the free energy difference between the liquid and the solid, okay, so there is a term which is proportional to the volume term. Okay. So you say that the bulk term, okay, so this is the bulk term. Okay. So the bulk term, that means the free energy of the solid is less than that of the liquid. So if you have a bulk solid, okay, then it will have a lower free energy. However, there is an energy cost to form this interface which is proportional to the area. So this is your volume, and there is a cost that is proportional to the area. Okay. Now, it turns out that if you have a very small crystal, okay, then this area term dominates, and actually the free energy for a small crystal becomes positive. Of course, if you have a large crystal, then the volume is much bigger than the area, and so the free energy will be negative, and you will form a crystal. Okay. So, what that means is that this free energy depends on the size of the crystallite. If you assume, for example, that you have assuming spherical nucleus, okay. So, this little piece of crystal is called a nucleus. So, if you assume that it is spherical, okay, then the volume goes as r cube. Okay, it is 4 by 3 pi r cube. So, in other words, it is proportional to r cube. The area looks like 4 pi r square. So, it is proportional to r square. Okay. So you have a free energy for crystallization that goes like minus a r cube plus b r square, some constant, okay, some constant times r cube and some constant times r square. Okay. Now, if you plot this free energy difference as a function of r, what you will see is that when r is very small, then the r square is much greater than r cube. Okay. So the r square term will be important when r is very small. So, when r is very small, it will look like the r square. Okay. So, and this is a positive term. So, the delta G will actually be positive. Okay. But of course, when r is very large, then then the r cube term is much larger, and it will change signs and it will go like this, it will become negative. So, that means if you have this place where it crosses, the size is called RC. Okay, that means if you have a crystal, if you have a small piece of crystal whose size is less than RC, then the free energy for forming that is actually positive. So, it is unstable. So, you have to grow a crystal that is larger than RC in order for the crystallization to be favorable. Okay. And this phenomena is called nucleation, because you have to nucleate a crystal that is at least RC. So, RC is the critical size of the nucleus for crystallization. So, until you grow a critical nucleus of size RC, your crystallization will be very slow, it will not be favorable. Once you grow greater than RC, then the crystallization will be very rapid. Okay. So this is an example where the area term or the surface term actually does not favor crystallization, whereas the volume term favors crystallization, and the net effect is to have a nucleation barrier. So, we say that the delta G has to overcome this barrier for crystallization. In other words, you have to keep growing all these very small crystals which actually increase the free energy, okay, until you grow a crystal that is large enough. Okay. So initially, until this critical nucleus is formed, your rate of crystallization is very slow, and once you form this critical nucleus, then the rate of crystallization is fast. And this is something that you have seen in some of your chemistry labs, that initially the crystallization is very slow, sometimes you shake it or you stir it, and then the crystallization becomes fast. Okay. The last thing that I want to talk about today is the shape of crystals, or more you can say the shape of crystallite. That is, so when I say crystallite, I mean a piece of a crystal. So, if you are growing a crystal, then what is the shape? Is it like a cube, or is it like a hexagon? I mean, these are really looking at three-dimensional shapes. Okay. So you imagine objects. Okay. Is it an octahedron? What is the shape of the crystal? Okay. Now, what governs the shape of the crystal? So, the shape of the crystal is basically telling you which directions the crystal is growing. So if you imagine that you have a liquid all around, Okay, you have the liquid around, and a small piece of the liquid has crystallized. So, you are looking at crystallization from melt. So, you have liquid all around, and a small piece of it has become a crystal. Okay. Now, the question is how does the crystal grow? Okay. Now, if you look inside the crystal, okay, then it has an ordered arrangement of atoms. Okay. So that means the atoms in the crystal are ordered in some way, and therefore, so for example, if the atoms were ordered this way, I will just take an example. If the atoms are ordered in this way, okay, and just extend it a bit more. I am deliberately showing a certain so if you just imagine a centered square lattice, okay, and this is a piece of a centered square lattice. Let me outline it by this green color. This is a small piece of a crystal of this square lattice, and just for illustration I am considering a 2-dimensional crystal, but you can do the same in 3 dimensions. What you see is that because of this ordered arrangement, you see that this direction is different from this direction, and this direction and this direction, all these are different directions. Okay. Now, you can see that these 2 directions are actually equivalent, okay, in the sense that if you look at the atoms, arrangement of atoms in this direction and this direction, it is the same. Similarly, these 2 directions are equivalent and these 2 directions are equivalent. However, if you take these 2 directions, they are not equivalent. Similarly, these 2 directions are not equivalent. Okay. So, in other words, due to the ordered alignment of atoms, the crystal has different directions. And now the question is, if this piece of crystal is lying inside a liquid, then atoms will deposit on all sides, okay, but there will be certain preferred phases in which the atoms will deposit faster. Okay. So, they might prefer to deposit on this phase, okay, and so certain directions of the crystal will actually grow faster than certain other direction. So, in other words, the rate of crystallization depends on the direction. So, the crystallization might be faster along one direction and might be slower along the other direction. So, let us take this crystal again. So, let me call this direction as A and this direction as B. Okay. Now, if the rate of growth is faster along B and slower along A, okay, and this is also I am just taking a square symmetry. So, all these directions are A. Okay. Now, if the rate of growth is faster along B and slower along A, then what will happen is that this B will move a lot faster, okay, and eventually, and this A is moving a lot slower. So, since B is moving a lot faster, okay, you will deposit these atoms, and finally, you will end up B will completely disappear. In other words, this crystal, if you have something like this, so it is growing fast along this direction and slowly along these 2 directions, okay, then eventually it will go to something like this, and it will just grow along this direction. Okay. So, in other words, the crystal will end up with a certain symmetry. So the shape of the final shape of the crystal that you get, or the crystallite, okay, that depends on which directions the growth is fast and which direction the growth is slow. So, this particular phenomena where certain phases of the crystal, so when you grow this crystallite, you see only certain phases, you do not see all the phases of the crystal, you do not see it growing along, you do not see other phases. So, if you take any crystallite, it has a very specific shape, okay, and these are called these phases of the crystal are referred to as facets, okay, and if you take any crystal, in fact there are crystals of very beautiful shapes that you can see at I mean, if you just search on the internet, you'll see very nice pictures of crystals of different shapes. Okay. And what I wanted to say here briefly is that the shape of the crystallite is really a function of which directions grow fast and which directions grow slow. Okay. There are other factors governing the equilibrium shapes of crystals, okay, which I won't talk about in this lecture. Okay. So, with this I will conclude the lecture for I will conclude this third lecture of the first week of this course. Thank you.